Welcome to A-Level and AP Physics. In today's lesson, we will discuss a typical type of question on astrophysics from March 2022, paper 4, variant 2. In this lesson, we will discuss how to state luminosity of a star. We will also understand what is flux intensity, radiant flux intensity. Then we will talk about Stephen-Boltzmann law. We will also discuss Wien's displacement law. And also, we will do some calculations based on these two main laws. For part A, we need to state what is meant by luminosity of a star. Luminosity of a star is the total energy of radiations emitted by any star per second. Simply, we can say this is the total power of radiations emitted by the star. And luminosity of a star, it is distance independent, means it does not depend on distance from star. This is how you can write down your answer. And this question has only 1 mark. If you have written this much, you will get 1 mark. Let's move on to part B now. For part B, it is given to us that luminosity of the sun is this. And the distance between sun and our planet is given is equal to 1.51 times 10 to 11 meters. Question is asking us to calculate the radiant flux intensity of the sun at the earth and give a unit with your answer. And so it's very straightforward question. Radiant flux intensity is equal to luminosity divided by 4 pi d squared, and d is the distance from the star. Now simply we need to plug in values and we can find out our answer for flux intensity. In this case, luminosity is given, that is 3.83 times 10 to 26 divided by 4 pi d squared. This is the distance from the sun, or simply you can say from the star. Distance is 1.5 times 10 to 11 squared. And if we solve this one, our final answer in this case will be 1340 watt per meter square. That's all what we have to do for part B. So simply we can write down here, this is the magnitude and the unit is per meter square, watt per meter square. This is the unit of radiant flux intensity. Radiant flux intensity, it depends on distance. If the distance from the star increase, then radiant flux intensity will decrease. And vice versa is also true. If the distance decrease, flux intensity will increase. If we talk about the marks, this question has only 1 mark. So that is B mark. If you have written this one, you will get B mark. And this question has 2 marks. So the first mark you will get if you have written this formula, and the final mark is the answer mark. If you have written the right answer with right unit, you will get the second mark. For part C, question is asking us to use data from B to calculate the mass that is converted into energy every second in the sun. But for luminosity of the sun is given, and the luminosity of the sun is 3.83 times 10 to 26 watts. It simply means that this is equal to 3.83 times 10 to 26 joules per second. Means sun is emitting this amount of energy per second. Now we need to find out the mass converted into energy. So we have to use E is equal to mc square. We have energy, we have to calculate mass. So simply we will say in this case mass is equal to E over C square. But the value of E is given to us, that is 3.83 times 10 to 26 joules per second divided by 3.00 times 10 to 8 square of this. If we solve this one, we will get our final answer 4.26 times 10 to 9 kgs. So this much mass is converted into energy per second in the sun. So this is what question was asking us to calculate. So our final answer is 4.26 times 10 to 9 kgs, kilogram. Our final answer has 3 SF because this quantity has 3 SF. So that's the reason our final answer is up to 3 SF. So you have to use 3 SF in this case. And this question has only 1 mark. If you got the right answer, you will get this mark. For part B, the radius of the sun is given. that is equal to 6.96 times 10 to 8 meters. We need to show that temperature of the surface of the sun is equal to this. So this question is quite straightforward one because luminosity of the sun is already given. So we can use simply Stephen-Boltzmann law, and according to Stephen-Boltzmann law, luminosity is equal to 4 pi r squared times sigma times T to the power of 4, and this is temperature in Kelvin. If we use SI units, our final answer will be in Kelvin. Now we need to calculate temperature from here, so we can write down temperature T. So simply we can write down temperature T in this case will be equal to luminosity over 4 pi r squared times sigma to the power of 1 by 4, and now we can just plug in values. Luminosity was given, that was 3.83 times 10 to 26 watts. We have to divide by 4 pi times r square. Radius is given, that is 6.96 times 10 to 8 square, and sigma is Boltzmann constant. Value of sigma is 5.67 times 10 to negative 8. So this is 10 to negative 8. Now if we solve this one, our final answer for T will be 5770 Kelvin. So temperature is equal to 5770 Kelvin. So this is what we need to show. And this question has only 1 mark. If we got right answer, we will get 1 mark. So this is our answer mark. For part E, it is given to us the lambda max of light for which the maximum rate of emission occurs, means the peak of this curve, the peak. So this is the lambda max. Not means the maximum value of lambda. In fact, this is the lambda at which the maximum rate occurs. So that is called lambda max, not the maximum value of lambda. Means the value of lambda at which maximum rate of emission occurs. That is called lambda max. Lambda max for the sun is given. This is equal to this. And temperature of the surface of the star Sirius is given. That is equal to 9940 Kelvin. But temperature of the surface of the sun we have already calculated in part D. That was equal to 5770 Kelvin. We need to find out lambda max for the star. For Sirius, means for this star we need to find out. We will use Wien's displacement law in this case. According to Wien's displacement law, lambda max T, this is equal to 2.898 times 10 to negative 3 meter Kelvin, not millikelvin. So lambda unit is meter. This is temperature. Temperature unit is Kelvin. So this is meter Kelvin, not millikelvin. Now simply we have to use this. So in this case we can say lambda max T. This is for Sirius. This is equal to constant, and if we use the same for the sun, that also will be equal to lambda max times T. It simply means that product of lambda max T is constant. So we can say for the star we can use 1. So I will use 1 here. For the sun I will use S. So this is TS. Simply I can say this is sun, this is sun. I'm using 1 here for the star. We have to find out lambda max 1. So this is lambda max 1. This is for Sirius. So this is for the star. So we can rearrange. We can say this is lambda max of sun times surface temperature of sun, and we can divide by surface temperature of the star. So I will write down star here, surface temperature of the star. Lambda max for the sun we have, that is equal to 5.00 times 10 to negative 7 meter, and surface temperature of the sun is 5770 Kelvin. We can divide by surface temperature of the star, that is 9940, and we can find our final answer. Our final answer in this case will be 2.90 times 10 to negative 7 meter, and this is our final answer up to 3 SF. This is final answer. Simply you need to understand how to use Wien's displacement law. The product of lambda max and temperature, not time, and temperature is always equal to this one. So that's the reason we have said lambda max times temperature for the star is equal to lambda max times temperature of the sun, surface temperature of the sun. These two, they are equal. And then we can find out lambda max for Sirius. So very straightforward question. If you follow these steps, you will get 2 marks. In this case, 1 mark will be for this law. If you have used this law, this will be C mark. And the final mark will be answer mark if you have got the right answer.